system. Okay, so let's see what are the various rules. Start with the first rule. The rule number one, that is the first step whenever we are plotting the root locus of a system, is first determine the open loop poles and the zeros of the system. Okay, from the transfer function which is given to you, determine the poles and zeros of that system. So first step is to determine all the open loop poles and zeros of open loop transfer function and plot them in S-plane. Okay, what you have to do in the first step, you have to determine all the open loop poles and zeros using the open loop transfer function of the system, and then plot all the poles and zeros in the S-plane. You know that the poles, they are denoted by cross sign, and the zeros, they are denoted by a circle. Okay, so this is the S-plane. S-plane consists of the imaginary and the real axis. It is the imaginary axis and it is the real axis. Real axis is the horizontal line and vertical line is the imaginary axis. This is positive imaginary axis, this is negative, this is positive real axis, and it is negative real axis. So we have obtained the poles and zeros in the first step, and then we will plot them on this S plane, and this pole, it is represented by cross sign, and the zero, they are represented by a circle. Okay, so this was all about the first step. Now the second step or the second rule is, so the rule 2 is related to the starting and the ending points of a root locus, that is from where the root locus will start and where it is going to end. So root locus, it is the rule number 2, it is the starting and the ending point. The root locus, it starts from the poles and it terminates at the zeros of the system. So the starting point of the root locus is the closed loop pole and the ending point is the zero of the system. The root locus, as we have said, that it starts from the open loop poles, and open loop poles, also we can say that it is, or k equals to 0. That is when the value of the gain, k is the gain of the system. So whenever the gain is 0, at that point, it's the root locus starts from that point and it terminates on either the finite open loop zeros or k equals to infinite. That is, it is starting from a open loop pole and terminating at open loop zeros, or we can say that it is starting from k equals to 0 point and terminating at k equals to infinity. So whenever we are plotting the root locus, just remember that it will start from a pole and it will terminate at a 0. Next is rule number 3. Rule number 3 is related to the number of branches of the root locus. We are plotting the root locus, how we are going to get that what will be the number of branches, how many branches this root locus is going to have. So rule number 3 is number of branches of root locus. Up till now, after this rule number 3, or we can say step number 3, we have just obtained the open loop poles and the zeros. Okay, so number of branches, it is determined by the number of poles and the number of zeros. If the number of poles means p, it is greater than the number of zeros, then the number of branches of root locus equals the number of poles. Suppose that a system is having number of poles as 5 and number of zeros is 3. So number of poles is greater than number of zeros, 5 is greater than 3. So the total number of branches of the root locus will be equal to the number of poles, that is there will be 5 branches. Now if the number of zeros is greater than the number of poles, then the number of branches of root locus equals the number of zeros. Okay, so if p is greater than z, then the number of branches equals to the number of poles. If z is greater than p, then the number of branches is equal to the number of zeros. Okay, let's take an example so that you can clearly understand it. Suppose that if p is equals to 2 and z is equals to 5. Okay, that is the number of poles of the system is 2 and number of zeros of a system is 5. So in this case, z is greater than p. Okay, so when z is greater than p, then number of branches will be equal to number of zeros. Now here number of zeros is what? 5. So there will be 5 branches. Now as we have said that root locus, it starts from the pole and terminates at 0. So root locus starts from pole. So the root locus starts from the poles and terminates at 0. Now here we are having 2 poles and 5 zeros. So 2 branches, they will start from the pole and terminate at the 0. And the remaining branches, they will start from a location of the open loop poles. Now what will be the case? We have total branches will be 5 and number of poles is 2. So 3 branches, remaining branches will be 3 branches. They will start from infinity while 2 branches will start from the open loop poles Okay, because for two poles we are having two zeros, so two branches will start from the open loop poles and the remaining three branches they will start from infinity. And how they are going to terminate? All the five branches will terminate at the five finite locations of. So all the five branches they will terminate at the five finite locations of zeros. So this was when the case when we have the number of zeros greater than the number of poles. Now take another example where the number of poles is greater than number of zeros. So suppose if P is greater than Z, that is P is equals to 5 and Z is equals to 3. So what will be that case? We have 5 poles and we have 3 zeros. So 3 poles are going to start from the poles and terminate at the zeros. So 3 branches. How many branches we are going to have? It will be equal to the number of poles. Number of branches equals to number of poles, and it will be 5. So out of these 5 branches, 3 branches will start from poles and terminate at zeros. Now we are left with 2 branches. So what these 2 branches they are going to start from the pole and terminate at infinity. Because we are having only 3 zeros, so the remaining 2 branches they will terminate at infinity. So this is how the number of branches and their locations will change according to the number of poles and zeros. If we are having Z, that is number of zeros greater than poles, then the branches which we are having, 3 branches they are start from infinity and 2 branches will start from the poles, and all these branches they will terminate at the zeros. If we have poles greater than zeros, then 3 branches will start from poles and terminate at the zeros, and the remaining 2 branches they will start from infinity and terminate at the start from the poles and terminate at infinity. So this was the rule number 3, that is the third step while we are plotting the root locus, and through this step we will be able to determine the number of branches of the root locus. Now let's see the fourth rule. Now rule number 4, it determines the direction of the branches. Okay, we have obtained the number of branches. Now what will be the direction of the branches? So determination of direction of root loci on the real axis. Locus is plural and root loci it is singular. So the branches of the root loci, what will be the direction of those branches on the real axis? So how we can determine it? A branch of root locus lies on the real axis if the total number of open loop poles and zeros to the right side of the point is odd. Okay, so a branch of root locus, it will lie on the real axis if the total number of open loop poles and zeros to the right hand side of the point is odd. Okay, that is odd number of poles and zeros are present on the right hand side of that point. Let's take an example so that you can understand it. This is the S plane, that is the imaginary axis, and this is the real axis. Real axis means sigma. Now plot the poles and zeros of a system. Suppose we are having a pole at the location +2, and here we are having a 0 at s equals to -1. We are having a pole at s equals to -2. So we are having two poles, s equals to -2 and s equals to +2, and we are having a 0, s equals to -1. This is the positive imaginary axis, negative imaginary axis. This is positive real axis and it is negative real axis. So we have plotted the poles and zeros of a system. Now to determine the direction, let's have check one and the other poles. First, we will start from this pole. We want to find the direction of the root locus for this pole s equals to -2. Okay, so if you want to determine the direction, take 2 points, one on the left hand side and one on the right hand side. Okay, left hand side point denoted as at P2 and this right hand side point denoted as P1. Let's check for each of these points that what will be the number of the poles and zeros on the right hand side of that point. Starting from this point, right side of this point, P1. Okay, so for point P1, point P1 is here. On the right hand side, if you check the total number of poles and zeros, we have 1 and 2, that is 2 poles and zeros. So 2 is an even number. So the direction of the root loci for this pole will not be in this direction because the total number of poles and zeros is even. So it will not be in this direction. Now check for point P2. We have here even number of poles and zeros. Now for point P2, if we check, let's check the total number of poles and zeros on the right hand side. We have 1, 2, 3. So there are 3 poles and zeros. So for point P2, we are having 3 poles and zeros on the right hand side. So point P2, we have odd number of poles and zeros on the right hand side. So the direction of the root loci for this pole s equals to -2 will be in this direction, because for point P2 it is having odd number of poles and zeros. So root loci will be in this direction, that is moving towards the -infinity. So it is the root locus plot for this pole s equals to -2. So in this way you are going to plot the root locus for every pole. Here the root locus, it is starting from the pole and it is terminating at -infinity. Okay, going towards infinity. Now if we check for this pole, again have 2 points here. This is suppose P3 and this is P4. Check for P3 the number of poles and zeros on the right hand side. It is what? 1. So 1 is an odd number. So for this pole, the direction of root loci will be in this direction. Okay. It will start from the pole and terminate at this 0. And if we check for point P4, the number of poles on zeros on the right hand side, it is 0. So it's an even number. So the direction of root loci will not be in this point, towards this point P4. It will be towards point P3 and it will start from the pole, terminate at 0. So in this way, you are going to find out the direction of the root loci on the real axis. Okay, so it was our step number 4. Now rule number 5 or step number 5. Now in step 4, we have determined the direction of the root loci on the real axis. Suppose there are two poles on the real axis which are adjacent to each other. So that is, in this example, we were having a pole, then a 0 and then a pole. If these two poles, they are adjacent to each other and the direction of the root loci for these two poles is towards each other, then these two root loci, they are going to coincident at one point. Okay, they are going to meet at one point and that point is called the breakaway point. So our rule number 5, it is related to the calculation of this breakaway point. So fifth is our breakaway point. And what is a breakaway point? When two branches move towards each other on the real axis, coincident point is called breakaway point. Okay, this is the real axis and imaginary axis. We are having two poles here. Okay, now for this pole, the direction of root loci is in this direction, and for this pole we are having the direction of root loci here. So these two root loci or these two branches of the root locus, they are going to meet at one point, and this point is called the breakaway point. This is our pole number 1 and this is our pole 2. So whenever two poles, they are adjacent to each other, that is close to each other, then the branches of the root locus from these two poles, they are going to meet at a point and that coincident point is called the breakaway point. So this breakaway point, it occurs between two adjacent open loop poles on the real axis. Now, how we can calculate this breakaway point? It can be calculated by differentiating the GS, that is the open loop transfer function of the system with respect to S, and that equating and after that equate that differentiation what you have get to 0. So breakaway point, it can be calculated using the formula, or what we are doing, we are differentiating dgs by gs, that is the open loop transfer function, with respect to it and equating it to 0. It can be calculated by differentiating open loop transfer function gs with respect to s and then equating it to 0. So when we differentiate this GS with respect to S, then we will get an equation in terms of S, and this equation will be equals to 0. Then simplify this equation and obtain the value of S. And that value of S, which you have obtained after simplifying this equation, will be the breakaway point. So the appropriate value of S is called breakaway. Okay, so whenever you are obtaining two adjacent poles, the branches from these poles, they will coincident at a point, and that point, coincident point, is called the breakaway point. How you are going to calculate it? You will differentiate the transfer function, open loop transfer function, with respect to S, and then equate that equation to 0. Simplify this equation to determine the value of S, and the value of S which you have got is the breakaway point. So this was our rule number 5. Now rule number 6. Now rule number 6, it is used in the cases when we are having higher values of the gain k. So as the value of this k increases, the root locus, it will move away from the poles. Okay, so as the value of k increases, the root loci moves away from the poles and zeros. Okay, so as the value of k increases, it will move away from the poles and zeros. So in that cases, that is for higher values of k, the root locus, it is approximated by the asymptotes. Okay, now in those cases where the value of k is high, we will use asymptotes for the plotting of the root locus. So for higher values of k, the root locus branches are approximated by asymptotes. What are asymptotes? So what is an asymptote? Asymptote is, suppose we are having a curve and we are having a line which is just going this side. This is a straight line and it is a curve. So the line which is just touching or just going cross this curve, it is called the asymptotes. So whenever we are having higher values of k, the root locus branches, they are approximated by asymptotes. Now these asymptotes or these straight lines, they are going to intersect the real axis at some point. So how we are going to determine the intersection point of these asymptotes with the real axis? We have a formula for it. So in this rule number 6, we are first having a point, that is the determination of intersection point of asymptotes with real axis. Now, first you have to determine that how many number of asymptotes we are going to have. So the number of asymptotes will be equal to the number of poles of the system. That is number of poles, if suppose there are two, a system is having two poles, then there will be two asymptotes. So number of asymptotes will be equal to the number of poles of the system. Okay. Now these asymptotes, what will be the intersection point of these asymptotes with the real axis? We are going to calculate it by using a formula. So this formula is x is the intersection point and it is given by summation of p minus summation of z upon p minus z. What is P and what is Z? P is the number of poles and Z is the number of zeros of the system. Summation of P means you have to sum up the values of all the poles of the system, and summation of Z means you have to sum up all the zeros of the system, and X is the intersection point. So let's define all these variables. X was what? Intersection point of the asymptotes with real axis. And what was summation of P? It was summation of all poles of open loop transfer function. And we have summation of Z, so it is summation of all zeros of open loop transfer function. Then we have P. P is the total number of poles and Z is total number of zeros. That is again writing the formula. We are having x equals to summation of p minus summation z upon p minus z. Let's take an example here. Suppose a system is having poles as s equals to 0, minus 1 and then minus 2. And zeros it is having as s equals to 1 and 4. Okay. So what is the intersection point here? We are having x equals to summation of poles means 0, minus 1, minus 2. So 0, minus 1, minus 2, what it will be? Minus 3. So minus 3 and then minus 0 summation will be 4 plus 1, it will be 5. Then how many number of poles we are having? We are having 3 poles and 2 zeros. So 3 minus 2. So x will be equals to minus 3 minus 5, that is minus 8 upon 3 minus 2 is 1. So the intersection point of the asymptote with the real axis is x equals to minus 8. That is at minus 8 the asymptote is going to intersect with the real axis. So in this using this formula we are going to find out the intersection point. Now second point in this is the angle of asymptotes. This asymptote, when it is intersecting the real axis, then it will be forming some angle with the real axis. So how we are going to determine that angle of the asymptotes? So our second point is angle of asymptotes. Asymptotes are drawn at point x. X is the intersection point, so we are going to draw the asymptote at this point, x point. So asymptotes are drawn at point x, making an angle with the real axis, and this angle is given by the formula we have 2m plus 1 into 180 degree divided by p minus z. So this is the formula for calculating the angle of the asymptotes. Here m is 0, 1, 2 till p minus z minus 1. Okay. P is the number of poles of the open loop transfer function and z is the number of zeros. Suppose we are having 4 poles and 2 zeros. So it will be 4 minus 2, that is 2. And here we were having 4 minus 2 minus 1, that is 2 minus 1. So 1. So m will be 0. Okay. So the value of m will be from 0 and to p minus z minus 1. And we will put this value of m here and then the number of poles in zeros, and then we are going to calculate the angle of the asymptotes. Okay. So this was our rule number 6. Now rule number 7. In the fifth point, we have determined the intersection of the branches of the root locus with the real axis. Now, these branches of the root locus, they are going to intersect the imaginary axis also. So, how in the rule 7, we are going to determine the point at which the branches of the root locus, they are going to intersect the imaginary axis. So, rule number 7 is to determine the points where the root loci branches intersect the imaginary axis. So how we are going to find out this point? Now, the point at which the branches they intersect the imaginary axis, we can get this is what? J omega, and this is our real axis. So whenever we put s equals to j omega and we will make the real part as 0, then that point will be this imaginary axis. So in the equation, in the characteristic equation, if we put s equals to j omega, then we will be able to get the point of intersection of the root locus with the imaginary axis. Because root locus is what? Root locus is the locus of the points we can say roots. So it is the locus of the points, so we can say the roots of the characteristic equation. That is, these are the points which are satisfying this characteristic equation. Now if we want to determine the intersection of this root locus with the j omega axis, that means that point is lying on that root locus and satisfying this characteristic equation. Now point on the imaginary axis will be s equals to j omega. So if we put s equals to j omega in the characteristic equation, then we will be able to get that point of intersection of the root locus with the imaginary axis. So there are two methods to determine this point. First method is to put s equals to j omega in the characteristic equation and make real part and imaginary part equal to 0 and simplify these equations for omega and k. Omega is the frequency and k is the gain. So put s equals to j omega in the characteristic equation. You are going to get an equation having both real and the imaginary parts. Take out the real parts, separate the real and the imaginary parts, equate the real part and imaginary parts to 0. You will get two values for s, and then simplify these equations, get the value of omega and k. So this is the point where the root locus branch, it is going to intersect the imaginary axis. Now second method is to use the roots stability criteria. Second is using the roots stability criteria. Root stability criteria we have already studied in our previous video. So using that root stability criteria also we can find the point of intersection of the root locus branch with the imaginary axis. Now take an example so that you will be able to understand how we are going to use these two methods to determine the intersection point. We are given the open loop transfer function of the system, that is GSHS equals to K upon S, S plus 2 and S plus 3. This is the open loop transfer function of the system. Now first we will apply our first method. In first method, what we were doing, we were putting s equals to j omega in the characteristic equation of the system. So characteristic equation is what? 1 plus gs hs equals to 0. This is the characteristic equation. Putting the value of gs hs from here, we are having k upon s, s plus 2, s plus 3 equals to 0. Solve it to obtain the simplified characteristic equation. We are having s, s plus 2, s plus 3 plus k equals to 0. So we are having s, s squared plus 3s plus 2s is 5s plus 2, 3, 6 plus 6k equals to 0. So we are having s cube plus 5s square plus 6s plus k equals to 0. So this is our characteristic equation. Now in this characteristic equation, put s equals to j omega. Okay. So j omega putting here, we are getting j omega cube. Then we have 5s square. So 5j omega square plus 6s means 6j omega plus k equals to 0. Now here we are having j cube. We know that j square is equals to minus 1. So here we are having minus j omega cube. J square has become minus 1, so we are having minus 1 and 1 j is left, so we have put j here. Now here we are having j square, so we will replace it by minus 1, so minus 5 omega square. Then we have plus 6 j omega plus k equals to 0. Simplify this further, we are having two constant terms without j, minus 5 omega square and k. So it will be k minus 5 omega square plus, taking j common from these two terms, it will be j 6 omega minus here omega cube equals to 0. So when we simplify this equation, we are getting two parts. This is our real part and this is the imaginary part. Equating these real parts and imaginary parts to 0, we will have k minus 5 omega square equals to 0, and here we will have 6 omega minus omega cube equals to 0. Take omega common, we will have 6 minus omega square equals to 0. So when we equate it to 0, we will get two values, omega equals to 0 or 6 minus omega square equals to 0. 6 equals to omega square. So omega will be equals to plus minus under root of 6. Putting here, solve this, we will have k equals to 5 omega square, and if we use here omega equals to 0 and omega equals to, so for omega equals to 0, k will be 0, and for omega equals to plus minus under root of 6, we will have k equals to 5 plus minus under root of 6 whole square. So it will be 6. So 5 into 6 will be 30. So we have got two values. One is for omega equals to 0, k equals to 0, and second is omega equals to plus minus under root k and k equals to 30. So this was the first method to obtain the intersection point. Now the second method is using the root stability criteria. So the characteristic equation which we have obtained was s cube plus 5s square plus 6s plus k equals to 0. This was our characteristic equation which we have obtained. So form the root array. Here highest power of s is cube. So we will start from s cube, then s square, then s1, then s to the power 0. Coefficient of s cube is 1. Then we will have another odd term coefficient, that is s to the power 1 coefficient is 6. Now s square coefficient is 5 and s to the power 0 coefficient is k. How to obtain s to the power 1 coefficient? Multiply this with this minus 1 into k divided by 5. So 5 6 are 30 minus 1 into k is k divided by 5, and this will be 0 because we are not having further coefficients here. Now how to obtain a coefficient of s to the power 0? Multiply this with this minus this divided by this. So we will having 30 minus k upon 5 into this k minus 5 into 0 is 0 divided by this, that is 30 minus k upon 5. So this and this, they will be cancelled out. So we are left with k only, and other coefficient will be 0. So our root array will be s cube, s square, s to the power 1, 0, 1, 6, 5, k, 30 minus k upon 5, 0, and this is k and 0. So this is our root array. We have formed it. Now to find out the intersection point of the root loci with the imaginary axis, then you have to put this 30 minus k upon 5 equals to 0. That is, this coefficient you have to put it equals to 0. So 30 minus k upon 5 equals to 0. Obtain the value of k from this equation. 30 minus k equals to 0. So k will be equals to 30. Okay, now the again, to find out the intersection point, what you have to do, you have to write the auxiliary or the subsidiary equation using this s square, that is the coefficient which you have put equals to 0. Just above that, whatever row you are having, write the subsidiary equation for that row. So using this row, we will write the subsidiary equation, that is 5s square plus k s to the power 0, and equate it to 0. Form the auxiliary or the subsidiary equation. So this will be 5s square plus k equals to 0. S to the power 0 is 1. So putting here the value of k as 30, we will get 5s square plus 30 equals to 0. So 5s square equals to minus 30 and s will be equals to plus minus under root of 6j. So this is the value of s, and we will get from here, if we take the value of omega, so omega will be plus minus under root of 6 and k is equals to 30. So this is the intersection point of the root loci branches on the imaginary axis, and we have used the two methods. First method was to put s equals to j omega, and second method is to use the root stability criteria. So this was our rule number 7. Now rule number 8. Now, if the poles of the system which we have obtained in the first step, if the poles are complex poles, then we will determine the angle of departure and angle of arrival for the complex poles. So, our rule number 8 is to determine the angle of departure and angle of arrival. So how we can determine these angles of departure and arrival? There are formulas for it. So the angle of departure, that is the departure angle from complex pole, is given by phi departure equals to 180 degrees minus phi p minus phi z. So this is the formula for the calculation of the angle of departure. It is equals to 180 degree minus phi p minus phi z. So what is phi p? Phi p, it is the phi p1 plus phi p2 till phi pn. That is the sum of all the angles subtended by all other poles. Okay, that is, suppose we are calculating the departure angle for a pole and which is p, then we will take the sum of all the other poles and sum of all the angles which are subtended by all the other poles. Suppose we are taking for s equals to minus 1 plus 2j, this is the complex pole. For that pole we are having other three poles also. So from the angle subtended by all the other three poles to this pole is the phi p, and phi z, it is phi z1 plus phi z2 plus till phi zn. That is sum of all the angles subtended by all all the zeros. Okay, so phi p, it is the sum of all the angles subtended by all other poles, and phi z, it is the sum of all the angles subtended by the zeros. Put the value of phi p and phi z in this formula to calculate the angle of departure from the complex pole. Now we have angle of arrival. So angle of arrival, if a complex zero is given to us, Okay, so phi arrival is equals to minus 180 degree plus phi p minus phi z. Okay, so this is the formula to calculate the arrival angle. Here again phi p, it is the sum of all the angles subtended by the poles, and phi z is the sum of all the angles subtended by all other zeros. So the difference between both the formulas is just for the sign. In phi departure angle, we were having 180 degree minus phi p minus phi z, and here we are having minus 180 degree plus phi p minus phi z. So just the difference of sign. Now take an example to understand that what is an angle of arrival and what is an angle of departure, how we are going to calculate it. Consider a pole zero diagram of a system. We have plotted the poles and zeros of a system on the real axis and the imaginary axis, that is on the S plane. Here we are having minus 1, minus 2, minus 3 and minus 4. Okay. Here it is 0, it is 1 and this is 2. So we are having a pole as S equals to minus 2. We are having a 0 at S equals to minus 4. Okay. And we are having complex poles here. Okay, so this system, it is having 3 poles and 1 0. One pole is at S equals to minus 2, and the other 2 poles, they are the complex poles. Okay, denote them as P1, P2, and here we are having P3, and this is our 0, Z1. Now we will calculate the angles for it. So the departure angle from this pole P1, it can be calculated by the formula, that is phi departure angle from pole P1. So departure angle formula is 180 degree minus phi p minus phi z. It is the departure angle formula. Substitute the value of the angles. Phi p, we have 3 poles, P1, P2, P3. So for P1 we will have phi P2 plus phi P3. Okay, and phi z will be what? Phi of Z1. Okay. Now how we are going to calculate it? We are having here, join these 2 points. Okay, then this angle and this angle. This angle is the departure angle from this pole Z1 and this pole P1. This is the 0 and this is pole. So this will be phi Z1. Here we are having the departure angle as phi P2. Okay, and this will be the departure angle phi P3 for this pole P1. Okay, so phi Z1 we can calculate from here, phi P2 and phi P3. Take the sum of these two and subtract minus phi Z1 from this, and we will be able to get, put all the values, we will be able to get the departure angle for this pole P1. So in this way we calculate the departure and arrival angle for complex poles whenever we are plotting the root locus of a system. Now next we have rule number 9. So rule number 9 is To determine the values of k on the root locus. As we know that the root locus, with the help of root locus, we can determine the value of k on all the points which are lying on the root locus. So how we will determine the value of k? We have a formula for it. K is equal to the So how we can determine the value of k on the root locus? We have a point P, and on that point we have to determine the value of k. So k is given by the ratio, or we can say that the product of length of the vectors drawn from the poles of the open loop transfer function to point P. We have to take the product of all the vectors length from the poles here and divided by product of lengths of vectors drawn from the zeros of the open loop transfer function to the point P. So when we take this ratio, we will be able to get the value of the K, that is the gain of the system on the point this P, which is lying on the root locus. So these are the 9 rules which we are going to use whenever we want to plot the root locus of a system. Now in this, have a note and keep this note in mind that when k is equals to 0, there will be no roots on the imaginary axis. That is, whenever you have to use the condition that k is equals to 0, just remember that there will be no roots on the imaginary axis. And second point is, if k is less than 0, then the closed loop system is stable. That means in the ninth rule, we are getting the value of k. So if we are getting the value of k as 0, then you can say that the system is not having any roots on the imaginary axis. And if the value of k is you are getting it is less than 0, then the closed loop system is unstable. And if k is greater than 0, the system is stable. So this we can say about the value of k, which we have obtained in rule number 9, that when k is 0, the system is having no roots on the imaginary axis. When k is less than 0, the system is unstable. When k is greater than 0, the system is stable. So these were the rules which we used while plotting the root locus of a system. You have to keep all these rules in mind, because step by step we are using them to solve the problems based on the root locus. I hope this video is clear to you. Thank you.